Unit 2, Kinematics, Differential Kinematics, Dynamics. In the previous lab, we worked on the static kinematics. So we talk about the position and the rotational metric and the displacement. Basically, we calculate the end result for the position of some point or some end effector location. In this lab, we are going to cover the differential kinematics that relates the velocity of the manipulator component. Differential forms of the homogeneous transformation can be used to examine the pose velocity of the frame. This method will be compared to the conventional dynamics vector approach. The Jacobian metric is used to map motion between joint and the Cartesian space, and the essential operation when curvilinear robot motion is required in the application such as welding and assembly. And the Jacobian metric will be covered in the next lab. Differential kinematics. Factors to determine the differential kinematics, including the frame-to-frame transformation, angular velocity, displacement velocity. So let's think about the differential transformations. First, let's look at the T-frame transformation, that is the orientation. So let's assume that we have a frame T relating a set of axes to the global base axis. So basically, you can think about the frame is frame 1, and then base is the frame 0 that we have in the previous lectures. Then the small differential displacement of the axis relative to the base axis result in a new frame such as this. So basically what this actually means is that the frame will change according to T prime equals T plus dt. And you can divide it by time and you will get it. So here you can continue use the P and Q point. So you may have 2 points, P and Q, and those two to form a homogeneous transform metric, and that one times T. So to derive that, you can see dt versus this one. You can derive the equation for it. You will find out that actually is a relationship of the d times t. Let's look at the next slide. So basically right here, you can see that the differential transformation dt equals t times a homogeneous transformation metric minus a identity metric, and you will get this. So basically this is the frame. And the differential transformation, you can say dt equals dt, that actually is the transpose of the t times d. These are actually equivalent. Okay, and what are these? You have delta d theta dp. P is the points are changing. So you will form a delta metric. The delta metric is the change of the positions. So let's go back to the previous slides. So here, actually, you can see that t prime equals t plus dt. So dt equals t prime minus t. So t prime minus t prime is a new frame orientation. So you actually basically can use the dp and dq, the original point for the p and q, with respect to the frame 1 and frame 2. So basically using the new frame minus the old frame, and then that will be the delta frame, the change of the frame. And this T actually is the frame location. So basically you can see that it is something like this. So it will be the H frame minus the identity metric, and then times a T. So the delta frame is formulated like this. So delta frame equals the homogeneous metric for the change between new frame original point to the old frame original point. And the transpose format is also okay. And here is the differential format for the data frame. And let's look at it. So velocity metric. So basically, there's a metric called screw velocity metric. In case of a pure rotation, so there's only rotation, there's no translation. The differential transformation depicted by D or transpose of D reduced to a screw rotational metric, rotational about a vector K. So there's a vector K, and then we rotate about the vector K. So that actually means that there is a vector K, and your frame actually rotate around the K. And here diagonal term being removed because there is a removal for the I. So basically, let's look at it. So the transpose metric you can write down like this. It actually is a PSPYPG. So PSPYPG is the point coordinate. Okay, and you originally have a orientation assignment by AXAYAG, BXBYBG, CXCYCD. That is the orientation. So basically, this is so-called the orientation metric. And then we take the derivative. You can have the inner product and the cross product, and two are of difference. Here we can calculate the inner product and cross product with the partial derivative, and it can be shown in this format. So these are detailed calculations. And if we have a P and Q and we change, so here you can derive the data move equals P prime minus P, and that would be equals T plus dt times W minus T, so that becomes dt. So dt will be the delta move metric, and then W is the point with respect to the original point, F1 frame, the original frame we are observing. So P equals TW. P equals PW. P is the original coordinate with respect to the frame 0, and W is with respect to the frame 1. So here we can calculate the so-called velocity as this. If we have the delta T approaching to 0, we can write down something like this. It actually is kg d theta, dt. It will be a so-called the angular speed, because d theta dt is omega. It's the angular velocity. And your dp dt will be the velocity in x direction. So the P itself, it actually is a point location. So dpx, dpy, when you take derivative, it will become the velocity of the observer velocity at the frame original point location. So here we have a case study. Let's assume that we have original point located at certain frame over here. That is 0, 0, 0. And here we have a frame C, and frame C's original point is 2, 3, 0. And these two have the same orientation, so XYZ the same. And we rotate around the Z axis. So basically, only XY change, and you will rotate like this. And the rotation speed is 2 radian per second. And the point that we are observing is P35. That actually is 35 relative to the original point, 23. And we actually have a speed of 22. So this one actually move out in the speed of 22 away from the frame C. And the omega is 2 radian per second. Under this condition, we can use the conventional solution. V0 equals V naught times omega x rho, and you can use that to figure out the speed. And basically, this difference in is based on you have two vectors. One is here to here, the other one is here to here, and you actually have the composition of these two vectors. You can calculate this. One is actually this -6 and -4. That actually is the rotational velocity for the frame. It's actually over here. And your total speed over here is based on the calculation. So you can go into the detailed calculation to get this one if you use a conventional vector approach. And we can actually formulate the dtw equals something like this. Let's assume that the w is actually the rho, the point, and your delta t is your dt matrix, and your delta is actually here 2 is the so-called velocity change that actually with respect to the frame. So your frame C, you have 2 away, and this speed is the radiant speed of 2 cosine theta. That the speed, angular speed. This one is the minus omega g, and here is omega g. So let's look at the matrix. They are corresponding to such a matrix. And here you put some vector because you are looking at the relative velocity over here. And you actually have the frame coordinate, the original point coordinate 2, 3 is shown up here, and we can calculate this one. So let's look at the Python code here. So Python coding. In the Python coding, we need to treat the delta matrix, the angular velocity matrix, and the orientation matrix, and the point W value, all in the HTM, the homogeneous transformation matrix format. So here you can see that the D we write down like this, and T we write down like this. Okay, one thing to take note of is actually this 2, 3 is the coordinate of the frame. So actually here the orientation is the same. So you get the identity matrix. And then this 2, 3 is with respect to this one. So this one in the homogeneous transform matrix, it becomes the so-called displacement. It's a displacement from here to here. Okay, and the D portion, you have a radian, so you have the minus omega g over here. So it rotates here in a speed of 2 radian per second. And here you have dx dy, dt, I'm sorry. Here you have dy dt. That's the away speed of the point in this frame. So with this different information, we actually can do inner product for the velocity matrix, the angular velocity matrix with the orientation matrix. We got dt. And then the point, we have 3, 5, 0, 1. This one very important. This one you must put a 1 over here. This one is the coordinate of the point with respect to the original point. And this 1, when we talk about the homogeneous transform matrix, you need to put SYG, and there's a 1. This 1 original from the W. If you look at the previous lab, we have this. So you can check the material in the previous lab. And with that, actually, you can perform D times T and then DWT, and you get DWT, and then you actually can print out the DWT. Okay, let's look at the code. So right here is the code. You have TW equals this, okay, dtw like this. Okay, let's run it. So here you got minus 1412 is the same as the note. So here, if you actually do not do tw first, instead you do dt first, and then you do use dt to do inner product with w. The result is identical. Thank you. Bye now.